6.4 is about simplifying radicals. We're going to start the lesson with a little vocabulary. So when you have a radical, there's usually a little number right outside of the radical on the left. That number is called the index. And we learned in the last lesson that something that is under the radical is called a radicand. So for this one, 81 is the radicand. When the index is invisible, so when you don't see anything there, there's really an invisible 2. So the index for this one is 2, and we know that the square root of 81 is 9. Alright, for the next one we have an index of 4. And if you break down 81, you get 9 times 9. And each of those 9s can become 3 and 3. So 81 completely broken down is 3 to the 4th. And because we have 4 of something, we can simplify that to 3. So whatever the index is, that's how many you need to bring one out front and get rid of the rest. Okay, so there's a little bit of debate over what A would equal there. Some people say A just equals the square root of B, while other people think you should put plus or minus. So you should have been taught earlier that when you are simplifying square roots, you only take the positive answer, but when you're solving equations, you put plus or minus. Okay, so because that's an equation that we're solving, I put plus or minus. But when we are simplifying, we're only going to take the principal square root. So I'm going to skip down here. The principal square root of 36 is 6. Right, now I'm going to go back to the middle box. For any real numbers a and b, and any positive integer n, so if you're trying to solve this equation, all you do is take the nth root of both sides. So to get rid of that exponent n, I take the nth root. And if I do that to the left side, I also have to do it to this side. So I'll write it over here. I have to take the nth root of b. Alright, now we're going to simplify some radicals. So for number 1, the square root of 25, that is not an equation. We are just solving, so we only put the positive answer, no plus or minus. For number 2, the square root of 25 is 5, but there's a negative already in the front. So we write negative and then 5. Again, the square root of 25 is just 5, but there's already a plus or minus there, so our 5 joins the plus minus that was already there. Right, for number 4, we learned that the square root of a negative number creates an imaginary number. So this one's going to be 5i. So far, for the first 4, we had an index of 2. Now we're going to use an index of 4. Alright, so if you break down 16, you get 4 and 4. And if you break those down, you get 2 and 2, and 2 and 2. So over here, we have the 4th root of 2 to the 4th, which can also be written as the 4th root of 2 times 2 times 2 times 2. So whatever the index is, That's how many you need on the inside to be able to simplify it. So we need 4 of something, we have 4 2's, so the final answer is just 2. Okay, the square root of 100 is 10, and there's already a negative out front. The square root of 121 is 11, and we join that with the plus or minus. Alright, so if you break down 64, you get 8 and 8. Two and 2 are prime. We can break 4 into 2 and 2 also. So if you break down 64, you end up with 6 2's. So you can pretty much divide an exponent on the inside with the index. So if I divide that, then I can take it out of the radical, and it will be 2 to the first power, and I don't need to write the exponent when it's 1. Okay, so for number 9, this is probably the most important concept of today's lesson. For number 9, the square root of x squared, most people would say that's x, but it's actually necessary to say the square root of x squared is the absolute value of x. However, when we go to number 10, we don't need absolute value. The square root of x to the 4th equals x squared without absolute value. So why do we need absolute value? The reason we need absolute value is because if x is negative, well, the square root of something is not allowed to equal a negative number. So, for example, let's say x equals negative 3. So, if x equals negative 3, x squared would equal 9. And we know that the square root of 9 is only the principal root, only the positive square root, so 3. But then this would be not true in this case, because when you take the square root, you're not supposed to get a negative answer. Alright, so the reason we need absolute value bars is because x might be negative. And then when you square a negative, it's going to be positive. And then when you square root that, you want it to still be positive. Okay. Over here, we don't need absolute value because x squared cannot be negative. So I'm going to answer these questions. Why no absolute value? X squared can't be negative. So when x is positive and you square it, it will be positive. If x was a negative number and you square it, it would still be positive. When x is 0 and you square it, it's 0. So you have to use absolute value when your answer to a square root might be negative. So if x is negative, well, we can't let this be negative because a square root can't be a negative, so we put absolute values. Alright, so when do we need absolute value and when do we not? You need absolute value, so you could write this somewhere. You need absolute value when there are 2 requirements. 1, the index is even. So you need absolute value bars when the index is even and the variable has, so I'm going to say the variable's exponent goes from even, and then after you simplify, it becomes odd. So again, you need absolute value bars when the index is even, and then you simplify, and the variable's exponent goes from even to odd. Alright. So for number 11, I can rewrite 16 as 2 to the 4th, which we simplified earlier, or we broke it down. And so now you could just divide the exponents by the index. 4 divided by 4 is 1, so we're going to have 2 to the 1st. 4 divided by 4 again is 1, so we're going to have a to the 1st. 8 divided by 4 is 2. So remember, it's the inside divided by the index. And if I simplify, I don't need the exponents of 1. This is going to be 2ab squared. But then we have to think about whether we need absolute value or not. So we don't need an absolute value for the 16 because 2 is obviously positive. It's only for variables that you sometimes need it. So look at the exponent for a. It used to be 4, which is an even number, and now it's 1, which is an odd number. So when it goes even to odd, you need absolute value. We don't need absolute value for b, because b went even to even. It was 8, and then it became 2. Alright, so for number 12, I just taught you guys you can divide exponents on the inside by the index. So that would give us 2x to the 2nd. And 2x times 2x is 4x squared. We don't need absolute value. For one, because x squared can't be negative. Also because the exponent went from even to even. Okay, for 13, we know the square root of 36 is 6. P to the 6th, remember there's an invisible index of 2. So p to the 6th, and then we could divide the 6 by 2, we get p to the 3rd. The exponent was 6, and then now it's 3. It went from even to odd, so we need absolute value around that part. Alright, so 14 has a negative already in the front. Square root of 144 is 12. The square root of w squared is w. And the square root of v to the 4th is v squared. Alright, did anything go from even to odd? The exponent on w was 2, and now it's 1, so we need absolute value. Okay, on the back, the first example, you don't need absolute value bars because the index is an odd number, and you only need absolute value when the index is even and the exponent goes from even to odd. Okay, so we'll get to some problems with an odd index when we get to number 19. So first, number 15, that has an invisible index of 2. So we're just doing a regular square root. The square root of 16 is 4. Square root of c to the 10th is c to the 5th. Remember, we're just dividing the exponents on the inside by the index of 2. So we're going to get d to the 4th. And now we're going to check. because the index is even, we have to check if any variables had an exponent go even to odd. So over here, that went from even to odd. So we need absolute value around c to the fifth. The exponent for d did not go even to odd. It went even to even. For number 16, again, there's an invisible index of 2. You can divide the inside exponent by the index. So this is going to become 3b minus 2 to the first power. Don't need to write the exponent when it's 1. However, the exponent was an even number 2. Now it's an odd number, so we need absolute value around this whole thing. Alright, so following the order of operations, this whole thing gets squared. So negative 5 times negative 5 is positive 25. The square root of 25 is only the positive square root, since we're simplifying. So the answer is 5. So again, you can take exponents on the inside and divide it with the index. So this is going to become negative 3c squared. Simplifying that, negative 3 squared is positive 9, c squared. Okay, so now we're on the problems with an odd index. So the cube root of 27 is 3, and if you don't see that right away, make a tree diagram. So if you break down 27, you get 3 to the third power. And again, you could just divide the inside exponent with the index. You get 3 to the first, and I'm not going to write the exponent of 1. On the last problem, we just saw that the cube root of 27 is 3. So this one will have the same answer, but then that'll go with the negative that's already there. For 21, when the index is odd and the radicand is negative, you don't need imaginary numbers because 3 negative numbers do multiply to make a negative. So this one's going to be negative 3. Negative 3 times negative 3 times negative 3 equals negative 27. Alright, 22 is similar. This has an answer of negative 3. And then we have to hit it with that negative. So this one is negative of negative 3, which is positive 3. Okay, so if you break down 8, you get 4 and 2. You get 3 2's. So what number multiplied 3 times makes 8? The answer is 2. What number multiplied 3 times makes 125? 5 times 5 times 5 is 125. There's a negative already in the front, so this one's negative 5. The cube root of negative 8 is negative 2. If you multiply negative 2 times negative 2 times negative 2, you get negative 8. And I'm going to divide the 6 by 3 and get a squared. Alright, for number 26, imagine that negative sign as a negative 1. The cube root of negative 1 is negative 1. And then I divide the 12 by 3 and get b to the 4th. Alright, so whenever the index is odd and the radicand is negative, your answer is just going to be negative. Alright, 32 is 2 to the 5th, so the 5th root of 32 is 2. We divide the exponents by the index, we're going to get x to the first and y squared. Right, we don't have to check for absolute value again because that's only when the index is even and the exponent goes even to odd. When the index is odd, you don't worry about it at all. Alright, so I'm just going to divide this one by that index since there are parentheses on the inside. So I know that 5a squared b is going to have an exponent of 2. And simplifying, 5 squared is 25. A squared squared is a to the 4th. B squared. Dividing the exponent by the index, we get 3 3y plus 5 to the first power. So the nice thing about this lesson was every exponent that we saw in the radicands was divisible by the index. And we'll learn soon what to do when the exponent cannot be divided evenly by the index.